So our next talk is from Orazio Gallo. How did I do on that name?
Yep,
Did I get it? All right, great. Who joined NVIDIA Research in 2011 and has worked on several computer vision and computational photography projects. In this talk, he's going to talk about the algorithmic processing that cameras perform to produce high-quality images and how this interplays with computer vision algorithms. Thank you.
Thank you. OK, let me restart my timer. All right, good morning, everybody, and thanks for coming to my talk. Thanks for the introduction. Before starting, I wanted to do some advertisement for my team. We do research at several levels of vision, from low-level vision, high-level, 3D vision, and of course, because we are NVIDIA, we do machine learning. And we are hiring, so if you think you can contribute to any of these fields, feel free to shoot me an email. A small disclaimer for this talk. I know there's going to be people who know way more than what I'm going to be talking about. The point of this presentation is to bring up some of the issues with imaging and get your mouth wet with some of the computational photography algorithms. So it's not by no means a technical deep talk. And it starts from the observation that for most of us, you press the shutter button on your camera and you get a beautiful picture like this. But to put things in perspective, really, this is more like what you should expect coming out of your sensor. And many of you may be familiar with this. And there's a lot of processing that goes on under the hood. And many of you who are computer vision engineers may wonder, why do I even care, right? I just care for the image. Well, first of all, I think it's incredibly interesting. So that's a good reason per se. But let's say that, let me justify this a little bit more. Let's say that you want to segment this image, right? And you can do so by simply picking a threshold, and you get your nice segments in the image. But if I add noise to the image, and I use a threshold that doesn't account for the noise level, things are not so nice anymore, right? Or let's say that you're given two images, and the exposure time is doubled between one image and the other. Because of all the nonlinear processing that goes into the camera, what can you say about the brightness of the patches from these two images? Can you say it's double? Well, we'll see that that's not the case necessarily. So, in this presentation, I will talk a lot about computational photography. So to put it in context, I would like to start by talking about a taxonomy of closely related image fields. Image processing, in my opinion, is the set of algorithms whose input is one or more images and output is, again, one or more processed images. And it's an old field, so there's a lot of stuff from denoising, super resolution. And on the other hand, we have computer vision, where the input is one or more images, and the output is some semantic information about these images, right? And so we have optical flow, we have segmentation, 3D scene reconstruction, and it's pretty obvious that the overlap between these two fields is significant, right? There's algorithms that, by my own definition, are in both fields. Think of deblurring, where the input is a blurred image, and the output is a deblurred image and the blur kernel, which essentially tells you about the motion of the camera while the picture was being captured. But what about computational photography? Well, one way to categorize algorithms in this field is to look at how they modify the imaging pipeline. And so you can think of, you can rethink how light is captured and brought to the sensor. And a typical example is light field photography. These are the Lytro camera and a Pelican imaging camera module. And here the idea is that instead of just recording the intensity of a ray, you also record the direction with which it enters the camera, right? And that allows a whole bunch of applications. Or you could play tricks with how you actively illuminate the scene. For example, in this somewhat dated paper by Microsoft Research, they proposed to take two images, one with a flash and one without. The one without is, of course, noisy, but captures the real underlying illumination of the scene, and you can combine them together in computation, obtaining the best of both worlds, essentially. Or you could think of novel sensors, and for this one, I want to mention very briefly this project that is coming out of Sheena Yard's group, and it's going to be presented in a couple of weeks at the International Conference of Computational Photography. Essentially, they came up with this super cool idea of having a silicon sensor which you can deform and still take pictures with it, right? So this sounds like a very cool idea, and I'm looking forward to what they can do with this. And then there's the more standard way, in the sense that it doesn't, we don't want to modify the hardware of the camera, we just change the way we capture images. This is what Ramesh Raskar from MIT calls epsilon photography, because you tweak the parameters while you capture images, and then that allows you to capture images such as an HDR image, for example. But you can also decide to replace the whole camera as we know it today, and this is a camera from a company called Light. It has 16 cameras on it, or 16 sensors with associated lenses, and their promise is to deliver DSLR quality in the form factor of a point and shoot. And we are all really excited to see if it can deliver on this promise. So having given this very quick overview of what you could do with computational photography, it's pretty clear that computational photography essentially stems and extends from the intersection of image processing and computer vision, right? Not only in the sense that there's overlap between the algorithms, but also because these fields share, one field will use algorithms from another field and vice versa. So now that I've given you an incredibly long introduction, here's what I would like to talk about. I would like to interpret the pixel value with you, which essentially means understanding what types of noises are involved in the image formation process, what happens at least at a very high level under the hood of a camera, and how you deal with it when you use RAW or when you use JPEG images. And then hopefully we'll have time to overcome some of the main limitations of standard cameras by means of computation. Okay, so let's get started. This is a very simplified diagram of what happens in a camera from collection of photons all the way to a digital value. And the reason why I show it like this is that I want to point out how many different types of and sources of noise are involved in this process. Many of these are beyond the interest of this talk and the audience, but we'll talk about some. I also wanted to point out that as a computer vision engineer, you can choose between using RAW images or JPEG images, and whether you use one or the other will determine, they will have advantages and disadvantages, but also you have to treat them differently in terms of data. So let's start from RAW images. If you want to work with RAW images, you need to understand because there's no denoising that goes on before you get a hold of the data, you have to understand how noise affects the image that you're looking at. And Fornation noise is something that Rob already mentioned. It's due to the quantized nature of light, as he said, and I'm going to repeat here a little bit. Essentially, it can be modeled as a normal distribution with a variance equal to the mean of the incoming photons, which means that the SNR, as Rob was pointing out, goes up as the square root of the signal. Essentially, the more photons you collect, the more noise, but the signal increases faster than the noise. And so you get pictures like the one on the right, where for a longer exposure time, the signal becomes dominant. So how do you leverage this knowledge? Well, you can do two things. You can do expose to the right, which means that you take the longest possible exposure before inducing saturation in the image, so you collect as many photons as possible. Or you can also leverage the stochastic nature of this noise and capture multiple frames and average them. What else? There's a dark current. This is due to the thermal energy in the sensor that allows electrons to be freed even though there's no incoming light photons, right? And then what I'm showing is a picture that I captured with a lens cap on, which looks black and perfect unless you zoom in, and I think you can see that there's a bunch of noise there. Projectors tend to always attenuate and make my presentations difficult. Oh, wow, and that. There you go. Right. So dark current is a function of sensor temperature and exposure time. And here what I'm showing is two plots of a dark frame, so a frame captured without light, incoming light. And you see that on the right, the temperature of the sensor is higher, and that means that the distribution gets spread out. And once again, in order to deal with this, you have two options. You can cool down the sensor, which is something that usually only high-end vision imaging systems can afford, or you can subtract a dark frame. You can remove this noise, and I'll show you in a couple of slides what I mean by this. And then, probably less complicated from a mathematical standpoint, pixels don't have the same response across the sensor. Lenses induce some vignetting effect, so some parts of the sensor see less light. And to deal with this, you can use a flat field image, which is an image of a uniform background. And you can normalize your image by this. And then there's radar noise, which includes a whole bunch of different components. Once again, you can minimize it by collecting as many photons as possible, and this also Rob pointed out. And you can also average frames to remove the stochastic component of this noise. So if we put all these things together, I think that, so this is a model for raw images where you have, do I have a pointer here? Here, okay. So you have an incoming irradiance E, which is integrated over time t, and then you have a constant offset, which is called black level. And this is your affine model for the incoming photons versus what you read at the pixel. And what you need to do after correcting for stuck or broken pixels, as I said, you need to capture a dark frame, in other words, a frame with a certain exposure time and no incoming light, a flat field image, which is the image of a uniform background, and then you can normalize or remove most of these noises by subtracting the dark frame and normalizing by the flat image, like I said before. And remember, always expose to the right. So if you do this, you're kind of like done with this part of processing for the raw images. But what about JPEG images? You may want to use JPEG images because, for example, you don't have access to raw images, or you may want to use them because you want to leverage the secret sauce that all the camera manufacturers spend so much time creating. And when I say JPEG images, I really mean any image that is compressed from the higher bit depth to 8 bits. And there's a whole bunch of things that happen under the hood. And going over all of them is beyond the scope of this presentation. I'm just listing some of them here. But what I want to point out is that all of this processing that happens can be modeled with a single transfer function, which is usually called camera response function, which has a compression function from the 10 to 16 bit input to an 8 bit output. And you need to know about this if you are looking at and comparing different images, in particular because this function changes from camera to camera. This is a depiction from a paper by Grosper and Nayar, and you can see that different manufacturers have very different camera response functions. What you can do is what is called radiometric calibration, which is essentially undoing this. Very briefly, if you have an incoming irradiance is the power per unit area at the sensor, for a certain pixel p, you integrate it over time. The camera essentially applies this camera response function f, and that's what you read at the pixel. And this function changes with both camera to camera and also scene mode to scene mode. In other words, if you're taking a picture of if you're taking a landscape picture, the camera response function may be different than if you're taking a portrait. And that's because they want to optimize the quality for the content of the image. And essentially, radiometric calibration is a whole bunch of different methods that usually take multiple images with different exposure times and then invert this function and use the knowledge that the irradiance should be the same for all of the images to estimate the camera response function. The literature is vast. I can refer you to this book chapter that I wrote with Professor Sen from UCSB, where we give an overview of this field. One thing that I wanted to point out, though, is that contrary to what many people believe, the reason why the compression function has this shape is not because CRT used to have a gamma or an inverse gamma, and so you want to do the opposite so you can compensate for it. No, the point is that the human visual system is much more sensitive to deviation and noise in the low range, so in the darker areas rather than the bright areas. And this kind of function, which will change, but will still have this characteristic that will allocate more bits to the darker regions versus the brighter regions. This function fits very well our perceptual abilities. So now if we go back to the example that I was saying before, if you double the exposure time, you cannot say much about how the patches change, but you know that if you perform radiometric calibration and you revert the processing that the camera did, they should be in the same ratio as the exposure times. Right. So this is all I wanted to talk about in terms of computational, in terms of nonlinear images. And now let's try to push a little bit these limits by means of computation. I will talk about three different things. One is dynamic range, which is very limited in cameras. Using raw images makes your life easier because they have a larger dynamic range. But essentially, we are very used to the fact that we can see a starlit sky almost as well as we can see the light of a flash. But the cameras, on the contrary, can capture only a small portion of this, right? However, I kind of lied. We cannot see a starlit sky at the same time as we see a flash. We need to adapt to either of those, right? And we can mimic their adaptation by taking multiple images and then combining them into a single one to generate a higher, or to capture and display a higher dynamic range. And this is, for example, what I did in this picture where I took this picture of on Westcliff in Santa Cruz, and I took one picture exposed for the sky, one picture exposed for the foreground, and I combined them into a single image. Now, what I want to point out is that because I'm merging these images, I need the pixels to be registered, right? I need one pixel in one image to see the same part of the scene as the corresponding pixel in the other image. Otherwise, I will get artifacts. And so that's the biggest issue in terms of high dynamic range imaging is the need for non-rigid registration because of both camera motion and subject motion. And here, I'm showing the results of a project that we did at NVIDIA where we dealt with this. You can see on the left, I have an input stack of differently exposed pictures where the subject was moving significantly. And our algorithm produces from that an output stack that is photometrically the same as the input stack, so the brightnesses are the same, but it's also geometrically consistent across images, right? And whether you use this or something else, you will have to account for this kind of problem. So this is for dynamic range. What about field of view? Again, a lot of overlap with the previous talk. If you get a 50 millimeter lens, you get a 47-degree field of view. If you double the field of view, the focal length, you reduce by half the field of view. So how do you deal with this? Well, it was something that we didn't discover recently. I really like this camera. It's called a wide lux camera, and essentially what it has is instead of a shutter, it has a slit that exposes the film as the lens pivots around the vertical axis. So it essentially can produce very wide dynamic range, very wide field of view images. Of course, the theme of this talk is to avoid modifying the hardware. So what you can do instead to extend the field of view is to do image stitching, which consists of taking multiple images of the scene and then find a way to combine them into a single panorama. And you might think that this is a solved problem and that this is old. And in fact, it is one of the first examples of computational photography algorithms. But it's coming back. And the reason for it is because VR and AR, virtual reality and augmented reality, are coming back, or are starting to become very important from a commercial standpoint. Here are a few rigs, camera rigs by Google, GoPro, and Jaunt. There are a lot of issues for synchronization. For example, the only one, the center one, the GoPro Omni, is very cool because they have pixel level synchronization. But the problem remains that you need to deal with parallax, right? All the panoramas that we're used to seeing are panoramas where you're very far from the subject, and therefore parallax, which is essentially due to the fact that you're seeing a scene from slightly different perspective, is still unsolved. You can rotate the camera around the center of projection, and that will solve the problem. If everything is infinity, you're fine. Otherwise, you have to do 3D reconstruction, full 3D reconstruction to solve the problem. It's actually a big issue. It seems solved, but it's far from it. So the last thing that we would like to extend is the fact that we have very limited control over the depth of field. So the depth of field, as Rob was mentioning, is the range in the scene that is in focus at any given time. And I'm showing here that among the other things, it's proportional to the distance, meaning that the farther you are from the object, the larger the depth of field. Which also means that if you're trying to do macro photography, you're going to have trouble. For example, in this case, the only part of the scene that is in focus is the tip of the, I don't know, you call it face, I don't know, the front of this insect. And much like we did for HDR, we can take multiple images and we keep focusing at different depths in the scene, and then we can combine all of them into a single one. Here I'm stealing blatantly this example from the work by Agarwal et al. From a few years back at SIGGRAPH. It was called digital photomontage. So by means of computation, by means of capturing multiple images and combining them together, you can extend the depth of field. But what about the other way around? Depth of field is also proportional to the aperture, the aperture number. So it's inversely proportional to the size of the aperture. So if you want to take an image that looks professional with a camera cell phone, it's going to be very tough because the aperture is really small. So the depth of field is actually going to be large. And in this case, you would like the background to be blurry and nice, right? So this is, I stole this picture from Mark Levoy, who developed this application called SynthCam. Essentially, what he proposes is to ask the user to move the camera around and capture multiple images while the camera is moved around. And then he essentially aligns all the images to one object, in this case, the statue in the front. And then he can average all the other images, obtaining a blurry background, so as to essentially simulate shallower depth of field, which, again, sometimes is what we care for. So with this, like my super incredibly fast overview of all the what I talked about is over, and I'm just gonna reiterate the most important take-home points. Many of you may be already familiar with this, but you have to make a decision between using RAW or JPEG images. I like RAWs because they are linear or affine, and they have a very nice dynamic range. JPEGs are better in terms of image quality. Whether you use one or the other, you'll have to do some processing on your own, or at least be aware of what happened in the image formation process. And then remember that if your camera has limitations, you don't need to change your camera necessarily. You can use computation to overcome these limitations. And In terms of computational photography, I want to make it clear, this is just the tip of the iceberg. But I thought that this would be the most appropriate topic for this kind of audience. And with that, I'm done. And that's my email address. You can take a picture of it.
Thank you very much.
Thank
Great
you.
talk.
Thank you.
I'm a long-time photographer, although looking at some of the pictures that you took, I'm a much lousier photographer than you are.
I stole many of them from good people. That's how
And
you
so I
do
know
it.
Photoshop fairly intimately. I've spent a lot of time in front of it, and it just amazes me the stuff that used to take me hours, if not days, assuming I didn't give up on Photoshop in front of a computer, can now be done instantaneously within a camera. So on that note, again, mics are at either end. Go ahead and queue up with your, we're going to take just a couple of questions before the break, but I'll start out with one. An increasing percentage of pictures are being taken not on standalone cameras now, but in camera phones, right? And cameras built into tablets. And I've noticed a trend towards dual sensor, dual camera arrays in the HTC One M8 a couple of years ago, and a couple of cameras that were announced at Mobile World Congress this year. What are the kinds of things that a dual camera setup allows you to do from a computational photography standpoint?
Right. That's a very interesting question. So it depends on what cameras you use, right? Some of the manufacturers that are coming up with new dual camera setups, they use, for example, a Bayer or a color image, RGB, a sensor on one side, and a gray level sensor for the other camera, which allows to capture stuff that the Bayer format cannot capture, a better resolution at the edges rather than better light efficiency because it's not throwing away any light. You can use different focal lengths in front of the two cameras, like essentially mimicking what the Leica camera is trying to do with 16 of these. You can of course do stereo and 3D reconstruction. I think that the list is very long. It's just that whoever, the successful player will have to find a good application for it. And I think the Leica camera found a good niche, like give me very high quality, DSLR level quality on a compact camera form factor. We'll have to see if they deliver. If they do, I think that that's probably the only use case that I've seen so far that is really compelling.
Okay, great, thanks. Let's look and see if we have any audience questions. All right, seeing none, thank you.
Thank you
very much.